Hey guys, this is Einar. I hope you're doing great today. Welcome to this tutorial where we're going to test for the difference between a sample and a population mean using a hypothesis test. Now, the formula that we're going to be using looks like this. Now, this formula creates a test variable, which is a standardized z-score, which will be located along a normal distribution like this. And we will be comparing our test variable scores, this value, to critical values along the normal distribution which we have specified right here. So before I start with anything else, we need to take a look at this formula. So what do we have here? Well, we have the sample mean, and because we're using a sample, we need to take the variation around the mean and the size of our sample into account, which is the same thing as our uncertainty, and that is conceptualized with the standard error in this case. So we have the standard deviation divided by the square root of n. We're taking our variation and our sample size into account. And then we're checking if this sample mean is different from a true population mean. And this is important because when we're using Greek letters like this, it means we actually have a true value. It's not an estimate, it's the truth. This will be a mean, but we don't need to take any variation or any sample size into account because we're not dealing with uncertainty. We have a true value here. So how can we exemplify this? Well, we have a data set right here, and I've created this data set myself, so don't think it's real or anything, but what we have basically here is a village of people, and loads of people here, that live close to a nuclear power plant. They live close to the Fukushima nuclear power plant. And these numbers here, the variable that we're measuring, is their attitude towards nuclear power. So 100 is they're really positive towards nuclear power, and 0 is they're really negative towards nuclear power. What happens? Well, then an explosion occurs. The village is burnt to the ground. Everybody runs away in fear and panic, and the population is split into different areas. But somehow, miraculously, we managed to get a random sample of these people from the village. Now, we couldn't get a hold of everyone. It was too expensive and too difficult to do in practice, so we had to use a sample. And we asked them again, what is your opinion about nuclear power now? Because we're guessing that their attitude towards nuclear power will change after the explosion. We're not saying right now that it's becoming more positive or more negative because we're using a two-sided hypothesis test. So it could be that their attitude becomes less inclined, less positively inclined, so lower values, or that they become more positively inclined towards nuclear power, so higher values. Just so you know that. Oh, I'm gonna delete that so you don't know that yet. Okay, so we have our two samples, or we have one sample to be true and one population, and we're going to compare these in order our test variable. So first we're going to need the true population x bar, the true attitude on average towards nuclear power before the explosion. So I'm going to write equal to average, oops, parentheses, and this data set is very large, so I'm going to use the cells instead of just selecting it manually. So I look at column C here, column A, column B, column C, and row 3, that's where my first observation is located. So I'm going to write here, I'm going to write C3, which specifies where our data set begins, and then a column. Now I need to find where my data set ends, so Excel knows where the data stretches. So I go down, oops, I went too far, there, go down all the way here, and I can see in column C, and row 1027, my last observation is located. So 1027, I need to remember that. We go up here all the way. And I write C1027. I close that parenthesis and I find that their attitude on average towards nuclear power before the explosion was 75 out of 100. Okay, so then the explosion occurs, the huge destruction all over the place, and we managed to get a random sample, and that's this part of the formula that we're going to be calculating now. So we need the n, because we're going to draw the square root of n here, so I'm going to count the number of observations in my sample. That's the first measure of uncertainty that we're going to take into account. Because we haven't asked everyone, we've just asked a few, we need to know, about how many people have we asked. That's very relevant to how certain we can be. We're also going to need the x bar because that's the measure that we're estimating. We want to know what is their attitude towards nuclear power after the explosion. So I write average. Average, I select my data set. And I close that parenthesis. For some reason there we go. And I find that after the explosion, their attitude is 67 out of 100. Now this is lower than before the explosion. So maybe we could say then that, okay, they have a more negative attitude towards nuclear power. Well, we can't yet, because we haven't asked everyone. We just asked 30 people, and it's natural for samples to vary. We don't know. We don't know for certain. So we need to take the variation around our X bar into account. And that is going to be the standard deviation, which is this part of the formula. So I calculate the standard deviation in my sample, like so, and I get a standard deviation of 19. The standard error then, which is this formula here, and it's the lower part of our test variable, is going to be equal to the standard error, see here, the standard error, so I select that, divided by the square root of n. So the square root of our sample n. Now this is important, the sample n. Okay, so I get a standard error of 3. This is our measure of uncertainty. And with that, when we have calculated that, we actually have everything we need in order to calculate our test variable. So I'm going to do that. It's equal to, first we're going to have our X bar minus our true population X bar. So I select my X bar there, minus the population average, there, close that parenthesis, and I'm going to divide this by the standard error. And I get minus 2.34. Now, I could actually just look at this diagram I created here in order to conduct an hypothesis test. We're not going to do that, later, but I'm going to do it now just to show you. Minus 2.34. Well, minus makes sense because they're more negatively inclined towards nuclear power after the explosion. We have a negative test value, you see, and this value here is smaller than that one, so that does make sense. So we're moving along this direction. And we're going all the way to minus 2.34. So 2.34, well, that's around here somewhere. These shades of red that I've marked here are the different confidence levels that we can have. So when we have 0.5% in each tail, we have a 99% confidence level. When we have 2.5% in each tail, all the way there, we have a 95% confidence level. So at a 95% confidence level, it seems that we are outside of what would be our confidence interval otherwise. So we are in the tail. Then we could actually refute the null hypothesis. But at a 99% confidence level, it seems that 2.34 is lower than this value here. So then we would have to accept the null hypothesis. But we're going to calculate this numerically, so it's really short. So I create a little table here, and I have two fields here for our null hypothesis. And the question we're asking ourselves is our test variable larger than, and then different critical values? And I looked these up in tables for you. Okay, so at 99% confidence level, is our test variable larger than 2.58 in absolute terms? Because it's a double-sided hypothesis test. We're not saying anything about negative direction or positive direction. So in absolute values, is 2.34 larger than 2.58? No, it's not. So in this case, we have to say that the null hypothesis is true, and we say that no, the change in attitude towards nuclear power is not statistically significant at the 99% confidence level. And what this in practice means that if I conducted my sample 100 times, in 99 of these cases, I would get a mean within a certain interval, and our test variable, it could be one of these means, so the difference could just be random. It could be attributed to randomness. However, if we lower our confidence level to 95%, we would get a critical test variable of 1.96. So we're, increasing the amount of samples in our tails here. We're going down to 1.96, so that's our critical value there. That's our critical value there, and these are the tails. And we ask ourselves the question, is our test variable larger than 1.96 in absolute terms? I check my test variable, minus 2.34, and I can say, yes, it is larger. And that means that we can refute the null hypothesis and say that at a 95% confidence level, we can say that this change, in fact, is not due to randomness. Now, it could still be. There's a 5 out of 100 chance that this change in fact is due to randomness, but that we're saying that chance is so low that we're actually choosing to draw the conclusion that a change has occurred, and that's what we mean by statistical significance. So that's important. We never know anything for sure when we're doing this type of social science, so bear that in mind. But we're saying that the risk of accepting a false hypothesis is so low that we're fine with saying that the change has actually occurred. And basically that's how you calculate hypothesis tests using test variables like this. We're going to move on to the next tutorial. Have some fun with this and try changing the values here and see if you can make the hypothesis true for falsifying the null hypothesis at 99% confidence level. What would have to happen here? Try different confidence levels and have some fun with this because it's a really exciting concept. So I'll talk to you guys later and have a really great day. Bye bye.